and so on. So he pointed out to me that I've been consistently making a mistake. This symbol here, I've been calling it eta, eta. It should be epsilon. Okay, so not that it really matters, but you might as well be correct. So this is the fifth letter of the Greek alphabet. So I'll be calling it epsilon. I've been talking about eta arrows, but they should be epsilon arrows, right? Okay. And what does epsilon represent? It's the empty string, right? The empty string. Okay. So that's also one of the simplest regular expressions. Just the empty string is a regular expression. And the third one here, just sort of jumping ahead a little, is the empty set, right? The zero with a slash through it. So those three are defined as the simplest regular expressions, and then from them you can build up larger, more complex regular expressions, and you can just keep going. You get very complex, involved regular expressions, but they're built up from these six components. Now you may ask, what are the other three? If R1 and R2 are regular expressions, then you can use the union operator. That'll give you, the result will give you a regular expression. So that's the fourth type, where you take the union of two regular expressions. Fifth type is when you take the concatenation of two regular expressions. Now these regular expressions may be of 1, 2, and 3. To avoid the possible complaint, critique, that if you're defining something in terms of itself, that's not good. That's a circular definition. But if you're defining a regular expression in terms of simpler ones, and right down to the simplest ones, then if those simplest ones are defined in terms of prior knowledge in some other way, like we know what a symbol of an alphabet is, we know what an empty string is, and we know what an empty set is. Those basic ones, the simplest ones, are defined in terms of something that does not involve regular expressions. Okay? So it's not a circular definition. Okay, and the sixth one, you just take the star. So the star of a regular expression is a regular expression. The concatenation of two regular expressions is a regular expression. And the union of two regular expressions is a regular expression. Okay? So if we can find a machine that recognizes each of these regular expressions, then we've proved that the language is regular. Because what is a regular language? It's a language that's recognized by an NFA. That was a former corollary. Was it 1.40? Yeah, that was a corollary we did earlier. 1.40, and that corollary says from memory. That's the problem. You're trying to remember all this stuff. Okay, I'll just get it from the book. 1.40. Corollary 1.40. A language is regular if and only if some NFA recognizes it. Okay, so it's an if and only if. So if we find an NFA for each of these 6 cases, then that means those NFAs recognize the regular expressions, and therefore the language that the regular expression describes is regular. Why? Because regular means that there's some NFA that recognizes it. Okay? Right, so let's get to the nitty-gritty of actually showing let's construct the NFAs for each of these 6 types of regular expressions. Now, the really simple one is let your regular expression just be a symbol of an alphabet, just A. It's just any symbol of some alphabet. So what would its language be? Now remember, a language is a set of strings. Well, it's a very simple string. It's just a string of length 1. Remember? Definition of the length of a string is the number of symbols in that string. Okay. Well, we only have a string of length 1. That's it. Okay. So it's a very simple language. It only has one string, and the length of that string is 1. Just one symbol. So there's your language. Very, very simple. So what would the corresponding NFA be for this language? Well, can you see it's just this? It'll be a two-state machine. Okay, so now here's your starting arrow. So it's the start state, and this is the accept state. Two circles as usual. And the transition arrow just has A there. So why would that work? Well, you start here, your symbol is A, and you go to here, to the accept state. And that's the end of your input string, right? Because it's at length 1. And that's it. You've ended in your accept state, and therefore the NFA, this big NFA, I'm exaggerating, recognizes this symbol, and hence this language, right? So that's pretty well it. Now there may be other symbols in the language, right? A is just one of them, and it's just to recognize that particular one. You have this machine. Now this machine here, this NFA, it's not a DFA. Why is that? Well, because there may be other symbols in the language. Now remember, to have for a DFA, you have to, for every, well, put this way, let's say your language has big N states. So, sorry, your machine, your DFA, has capital N different states. Okay, and let's say there are M symbols, different symbols in that NFA. Therefore, your DFA, your state diagram, will have to have big N times M, NM times. There will have to be that many transition arrows in your DFA. Okay? Well, that's not the case here, because there may be other symbols here. We've only got we've got two states, and only one output arrow. You have to have, for each state, the number of output arrows you need is the number of symbols in the alphabet. Well, there may be other symbols, and we've only got one arrow coming out. So this NFA here is not a DFA. Okay, that's just pointing. That's what it's saying here. Okay, now the full definition of this machine. Well, let's see. Now we've got two states, right? It's a start state and an accept state. So you could call that one Q1, Q2. So there's your set of states. That's your capital Q, right? The alphabet, whatever it is, sigma, transition function. Well, that's always the hardest part. So it's here, but we'll get to it. Do the trivial stuff first. Start state Q1, okay, pretty easy, and the set of accept states, capital F. Well, it's only one, so wiggly brackets to make it a set, and remember Q2, which is here, right? Now, okay, now get back to the transition function delta, usually the hardest part. Well, if we're in this starting state and in comes, the input string is A, then we want to transition from Q1 to Q2. Well, that's this. Okay? Your current state, input symbol, and the delta, your transition function, tells you what the next state should be. Well, we want it to be Q. Now, it's an NFA, right? So it'll be a set of next states. well, we've only got one, so it'll be a set of Q2. It's not just Q2, right? It's wiggly brackets Q2 because it's an NFA. If you're a bit fuzzy on that, go back and revise what NFAs are about. Okay, so that's understandable. Now for any other state, you want the output to be the null set. So for any I'm a bit fuzzy on this. If this little r, I assume, is a member of, he wasn't. This is Sipser not being clear again. I find I'm becoming a bit increasingly critical. Is sort of throwing details at you without explaining them too well. Okay, so what's going on here? So, presuming these little r's here, they're obviously states, right? That's the nature of the delta function. So, presuming these little r's are other states belonging to big R. Big R is a regular expression. So these other states of a machine, and these are other symbols belonging to big sigma, I assume. So if this state is not your initial state, then the output is the null state. So yeah, so if this R is not the start state and